If you've been following AI research lately, you've probably noticed a quiet but massive shift. We're moving past the era of just throwing more parameters and more compute at every problem. The bottleneck isn't just training anymore. It's inference. It's latency. It's the sheer cost of running these models at scale. And the researchers cracking this open right now are doing it with architectural elegance, not brute force. Let's talk about mixture of experts. If you've worked with large language models, you know that dense architectures route every single token through every single layer. That's computationally expensive, especially when you're scaling to billions or trillions of parameters. MoE flips that paradigm. Instead of a monolithic feed-forward network, you split it into multiple smaller expert networks. Each token only activates a subset of those experts during the forward pass. The routing mechanism, usually a lightweight learnable linear projection, decides which experts get called. This means you can scale model capacity dramatically while keeping per-token compute roughly constant. The catch is load balancing. If the router consistently sends tokens to the same few experts, you get stragglers, wasted capacity, and training instability. Modern implementations solve this with auxiliary loss functions that penalize uneven routing, plus top K gating where each token picks the two highest-scoring experts. The result is models that train on the same hardware, but achieve performance that used to require 2 or 3 times the compute. But training efficiency is only half the battle. Inference is where the rubber meets the road. And that's where speculative decoding has changed the game. Standard autoregressive generation is inherently sequential. You predict one token, feed it back in, predict the next. You can't parallelize it without breaking the causal mask. Speculative decoding bypasses that bottleneck by using a small, fast draft model to propose multiple tokens ahead of time. The large, accurate target model then verifies them in parallel. If the draft matches, you skip the expensive forward pass for those tokens. If it diverges, you roll back and continue normally. Mathematically, you're trading compute for parallelism, and because verification is batched, you often get 2 to 4 times faster throughput without touching the target model's weights. The trick is making the draft model cheap enough that the overhead doesn't cancel out the gains, which is why researchers are experimenting with distilled transformers, recurrent architectures, and even non-autoregressive sequence generators as drafters. Now you might be thinking, if we're optimizing compute and parallelism, why is latency still a problem? Because memory bandwidth is the real wall. Modern GPUs are compute-bound during training, but during inference, they're almost entirely memory-bound. You're fetching weights, activations, and KV cache entries from VRAM faster than you're processing them. That's why optimizations like PagedAttention and KV cache quantization are getting so much attention. PagedAttention borrows from operating system virtual memory, treating the KV cache as a set of non-contiguous blocks. It eliminates internal fragmentation, allows dynamic allocation, and dramatically reduces memory overhead. Meanwhile, researchers are pushing KV cache compression through techniques like H2O, which prunes redundant keys and values based on attention entropy, and streaming LLM, which preserves only the most recent tokens and a small set of attention sinks. These aren't just incremental tweaks. They're fundamentally changing how we think about memory-bound generation. So where does this leave us? The frontier of AI research isn't just about bigger models anymore. It's about smarter routing, parallel verification, and memory-aware architecture design. The models that will dominate the next cycle won't necessarily be the ones with the most parameters. They'll be the ones that route efficiently, verify quickly, and respect the physical limits of hardware. And for anyone building or deploying AI systems, understanding these mechanisms isn't optional. It's the difference between a prototype that runs on your laptop and a production system that scales to millions of users. If you want to dig deeper into the papers, benchmarks, and code implementations behind these techniques, I've linked the key research and open-source repositories in the description. Check them out, experiment with the routing strategies, and let me know in the comments which optimization you think will have the biggest impact on real-world deployment. I'll see you in the next one.